Hello! We are in the middle of discussing an outline for the proof of Nash's theorem, which states that every finite strategic game has a Nash equilibrium. We want to use Brouwer's fixed point theorem to prove this, which states that any convex and compact set X in a finite dimensional space, any continuous function that maps X to itself has a fixed point. Last time, we have established that the set of all strategy profiles delta is convex and compact. We now need a function f that maps delta to delta to relate fixed points and Nash equilibria. Here is the main idea of how we can define f. Given the strategy profile x, which is x1 to xn, a player I will look at possibly switching to a pure strategy to gain utility against x minus I. If a pure strategy S improves this utility, then player I wants to shift their probability distribution so that S receives higher probability. So this is what the function is going to do. The function will take our strategy profile x and map it to another strategy profile where each player improves their utility. Let's have a look at the rock, paper, scissors example. Each player's mixed strategies can be represented by a triangle with the pure strategies rock, paper, and scissors as the vertices. In our first instance, suppose both players play rock as a pure strategy, which is represented by these 2 points here. Currently, both of them have utility 0, but they can increase utility by moving towards paper, so that's what the function does for them. In our second instance, suppose that player 1 plays rock and player 2 plays paper, represented by these 2 points. Player 2 has utility 1, so they cannot improve their utility. On the other hand, player 1 has utility minus 1, so they can improve utility by 1 if they move to paper. Or they can improve their utility by 2 if they move towards scissors. So the function will move player 1's profile towards both paper and scissors, but more so for scissors than paper. So given such a function, what is the meaning of a fixed point? It means that no player can improve their utility by switching to another pure strategy of their own. So it must be a Nash equilibrium. We now formally define the function that we will be using to apply the fixed point theorem. First, we define a phi function which records the improvement of a player's utility in switching to a pure strategy. Given a strategy profile x, a player I, and a pure strategy S for player I, we define phi Si of x to be the maximum of 0 or the utility of player I when they switch to S minus the utility in x. This means that if playing S increases utility for player I, then phi Si of x represents this increase. Otherwise, it is 0. For player I and for those pure strategies S that improve the utility, meaning phi Si of x is greater than 0, we want to increase the probability that we assign to S. In particular, we want to replace xsi by xsi plus phi Si of x. However, this causes a problem. So, what is the problem and how can we fix it? The problem is that the sum of the probabilities is greater than 1. To solve this problem, we can normalize the probabilities by dividing the sum of the new probabilities. That is, the sum over all pure strategies for player I, S prime, their new probabilities, x s prime I plus phi s prime I of x. The sum of the xi's is just 1, so this is equal to 1 plus the sum of all the phi values for I. So now we can define our function f, which maps delta to delta, by f of x is equal to x bar, where for each player I and strategy S belongs to Si, the new probability assigned to S for player I, x bar Si, is equal to this expression here. You can quickly verify that f of x is in delta. Every player still has a proper probability distribution. Going back to the rock, paper, scissors example again, where player 1 plays rock and player 2 plays paper, the strategy profile is 1-0-0 and 0-1-0. For player 2, the phi function is always 0, because you cannot increase utility by switching from paper. For player 1, the phi function when switching to rock is 0, the phi function when switching to paper is 1, and the phi function for switching to scissors is 2. So the new strategy for player 1 is, for rock, it's 1 plus 0 over 1 plus 3, which is 1/4. For paper, it is 0 plus 1 over 1 plus 3, and that's 1/4. And for scissors, it's 0 plus 2 over 1 plus 3, which is 1/2. So the new strategy profile is f of x, which is 1/4, 1/4, 1/2, and 0-1-0. As you can see, the probability of rock is reduced, and the probabilities for paper and scissors are increased, more so for scissors than paper. We are now a few short steps away from completing the proof of Nash's theorem. Given a strategy profile x, consider the phi function and the f function defined above. We see that f is continuous since phi is continuous. Together with the fact that delta is a convex and compact set in the finite dimensional space, we can use Brouwer's fixed point theorem to say that there exists a strategy profile x hat such that f of x hat is equal to x hat. It is a fixed point. We now prove that x hat is a Nash equilibrium by showing that the strategy that player I plays, x hat I, is in the best response function of the remaining players' strategies, x hat minus I. For player I, we let S be a pure strategy for player I such that x hat Si is greater than 0, meaning player I has assigned positive probability to strategy S, and the utility for player I of playing S is at most the utility of x hat. As an exercise, show that such a strategy S exists. Because player I gains no utility by playing S, phi Si of x hat is 0. Since x hat is a fixed point, we can say that x hat of Si is equal to f of x hat of Si, which is equal to x hat Si divided by 1 plus the sum over all the strategies of player I, their phi values for player I. Since x hat of Si is greater than 0, the only way for the two sides to be equal is if the denominator is 1. So that means the sum of the phi values must be 0. But phi is always non-negative, so the phi value is 0 for all the strategies for player I. In particular, this means that playing any pure strategy for player I does not improve the utility from x hat. So, playing x hat I gives the highest possible utility against x hat minus I. So x hat I must be in the best response against x hat minus I. And since this holds for all players, x hat must be a Nash equilibrium. And that completes our proof of Nash's theorem. As a final note, this proves that a Nash equilibrium always exists, but the proof does not show us how to find such a Nash equilibrium, as it depends on Brouwer's fixed point theorem. And this is the end of the section on strategic games.